Thank you for the introduction. So, as introduced, my name is Aleksander Boruguszewski, and I'll be presenting a case for DOT paper, which is joint work with Radosław Waśko, Yixin Xu, and Lionel Perrault. And I'd like to begin with a problem statement. So there is a development that we are recently seeing in languages which support object orientation, and it is that they are adding support for functional programming features, and concretely, they are also adding support for pattern matching in some form, in one form or another. Java, C#, and Kotlin now all support pattern matching with type case patterns, which means that we can have a pattern which checks if an object is an instance of a particular class. Scala and Ceylon have supported full-fledged pattern matching from their early beginnings, and from the slightly more exotic examples, TypeScript and Flow support flow-sensitive typing aware of the instance of operator, which is just as expressive as having type case patterns. And what's interesting about this is that in most of these languages, we will actually get puzzling compiler errors merely because we have combined generic classes with pattern matching. And Scala is an exception here. So let's take a look at an example here. Let's say that we are a PL student and we are trying to have an assignment where we need to work with a simple expression type, right? So say that we have conditionals and integer addition. So we start by defining a trait, expr of A. We define a single subclass for it, an intlet that extends expr of int and that holds a single value of type int. And then we try to evaluate an expr of x, right? And we do that just by matching on it. We figure out if it's the literal, and if that's the case, we return the literal value, right? So this seems obviously correct, and Scala will accept this code as well typed. However, if we try to do the very same thing in Kotlin with a very similar looking snippet, it will get rejected. And what Kotlin will tell us is that we are returning an int where an x was expected. Okay, so I hope this is puzzling, right? Because the example, it seemed obviously correct, and yet what Kotlin is saying is also technically correct, right? So what's actually going on is that it takes just a bit of sophistication to convince the compiler that this example is actually correct. And here is how the Scala compiler reasons while typing the pattern match case. It's a bit like this. We are checking, we start with an expr of x, and we are checking if it is an instance of intlet, right? If it is, that object is also an instance of expr of int, since that is what intlet extends. Now, since expr is invariant, that must mean that x is equivalent to int, I mean, for some reasonable definition of equivalence. And that means that eval is actually well typed. And yet, Kotlin actually rejects it, as well as most of the languages from my first slide. So that actually seems like a bit of a problem, because it really seems inevitable that examples like eval will occur in practice. I mean, some forms of data are naturally like expression. I mean, what expr is just a typed AST. Anytime we have a typed database query, that's basically expr. Anytime we run this database query, that's eval, right? And in addition to that, generic classes are used all over the place in object-oriented code bases. So as language developers will try to experiment with the new ability to pattern match on these generic classes, they are likely to find examples like eval on their own. Okay, so say that we do want to support such code. Now the question is, what sort of reasoning can we perform? We need some foundations which will tell us what is and isn't sound. So in functional programming, we have GADTs, which would let us define a function like eval in Haskell. However, now the problem becomes that GADTs typically aren't studied in combination with subtyping. So here is an illustration why this is a problem. What we will see here is an issue that was pointed out in 2013 by Paolo Giarrusso, so almost 10 years ago. We have an example. We start with a covariant expr, and we have a const subclass. which generalizes int lit to constants of arbitrary type B, right? We define eval on this version of Expr, and so far so good, everything actually works. But what used to be allowed back in 2013 is that we could define unsound, and if we tried to evaluate it, we expected an int, and we actually got a string, right? And the point that I'm trying to make here is that this problem occurred specifically because of the combination between this GADT-like reasoning that Scala's compiler was performing and inheritance and variance and subtyping. So any foundations that we want for our reasoning, they should be able to account for this, right? They need to be able to inform us why we should reject unsound. And in addition to that, they should scale to be suitable as a basis for a complete object-oriented language, because we don't know what other feature of the language might be unsound in combination with our reasoning. So I've actually been chipping away at this problem with various side projects for basically the last 4 years while working on the pDOT compiler in Martin Underski's laboratory. And one of the conclusions that I've reached is that we can have foundations which satisfy this criterion we set for ourselves, and yet which remain remarkably simple. Okay, so let's see what this form of reasoning will look like in these foundations. So our reasoning boils down to this simple OO-centric idea of type parameter values. And it comes down to this one observation that type parameters can be thought of as though they were fields in two senses. One, when we instantiate a generic class, we also need to initialize its type parameters. And two, we can address the types which were used to do so by selecting the type parameter from an object. So here is an illustration. We have a generic class, aptly named generic. We create an instance of it, a new generic of int, and we assign it to G. And here we would say that the value of A in G, spelled as G.A, is equal to int. And continuing, all parameters need to be initialized, no matter what variance they have, and no matter if they are directly defined in the class or if they are inherited. On the next example, we see a covariant expr together with intlit. We create an instance of intlit and we assign it to L. And at this point, we would say that L.A, so again, the value of A in L is equal to int, right? And that's because of the extends clause of intlit. So it acts as though it was a constructor call. However, one thing that we need to be careful about is that type arguments are only bounds on type parameter values. So here we have a variable L2 of type expr of any. And now, based on this type, we would at most say that L2.A is a subtype of any. Why? Because L2 could actually be L, which would make L2.A be equal to int, right? So the any in expr of any is just an approximation on the actual type parameter value, naturally, because it could have been widened by subtyping. And this form of reasoning about type parameter values can help us already convince ourselves that eval remains well typed, even if we make a covariant, even if we make expr covariant. So we see an appropriate example, and here is how we would reason about it. In the body of eval, based on the type of E, we would say that E.A is a subtype of X. Then, in the pattern match case, we would also say that E.A is equal to int. Why? Because the pattern has performed a dynamic type test, right? It has tested that our E is actually an instance of intlit, and intlit initializes A to int. And based on these two pieces of information, we can reconstruct a lower bound for X. Right? We can say that int is a subtype of X, which makes eval well-typed. Okay, and what we have seen here is actually a key feature of reasoning about type parameter values, namely the fact that it lets us reconstruct subtyping relations based on information uncovered by dynamic type tests. And based on this notion, we refer to our form of reasoning as subtyping reconstruction. Okay, on to the formal foundations. So as the formal basis for subtyping reconstruction, we have developed the cDOT system. Now, as the name suggests, cDOT is part of the dependent object types family of formal systems. It builds on pDOT, presented at OOPSLA here a few years ago, and pDOT itself was based on the original DOT system. And that system was proposed and used as formal foundations for Scala 3, concretely, which makes cDOT suitable as a basis for fully featured object-oriented languages. And on that note, these languages, they have a tendency to have a lot of features, right? I mean, they have nominal classes and they have generic classes with type parameters. There is variance, there's applied types with type arguments. And finally, as we have seen, we can also think about type parameter values. Now, cDOT and DOT systems in general try to do with a minimum of formal concepts. And so all the concepts on this slide are formally represented in cDOT by structural types with term and type members, and nothing else. So we will introduce this representation gradually, at first by using Scala syntax. So here we see an example type assignment in cDOT. On the left-hand side, we have an object literal with two members, a term member value, also known as a field, and a type member A. And what we also see here is that both the members need to be initialized in the object literal. And we would type this object literal with an intersection of two structural types, one for each member. Now, the way we represent classes is a bit more complicated, so we will spend a bit of time on this slide. So the way we would understand these two definitions of expr and intlit is they are contained in some global scope, in some global package. And formally, the way we represent that is that we have some global module G. The name here isn't very important. Which contains definitions of our types, of our data types. Our expr is translated to a type member, a G expr, which has an upper bound, and that upper bound tells us that G expr has a single type member A, right, which naturally represents the type parameter A. In the comment, we see how an applied type would be translated. So we see that, as an example, expr of int would be translated to an intersection between G expr and a refinement which adds an upper bound on A. And the upper bound part here comes from the fact that expr is covariant in A. If it was contravariant, we would have a lower bound. If it was invariant, we would have equality. And what we also see here is that outside of the body of G, we do not know if G expr is equal to any other type. We have equality in the body, but not outside, right? So that means that in general, we don't know if G expr is equal to any other type, so we cannot substitute it with anything else. So it means that it is nominal. And that idea, that sort of encoding of nominality, has been present in the DOT family since the original DOT. Okay. Now, intlit is translated into two members. The type member has an upper bound, which tells us that intlits have a value field of type int, and they inherit from G expr by initializing A to int. And the term member, which is the new intlit method, is a formal representation of the constructor for the intlit class. And the implementation of this constructor is quite simple because we just return a new object literal, which is appropriately initialized. Okay, so let's now take a look at how we would type eval in cDOT. So here we see eval, which is expressed using our representation of classes. And again, just to emphasize, this snippet uses Scala syntax, but it corresponds one-to-one to a well-typed cDOT term. And if we wanted to formally model the Kotlin snippet, we would do it with the exact same term. Okay? So let's take a look at what makes this example well-typed. The interesting part is, of course, how we type the pattern match case. So in there, the type to which we bind E1 is an intersection between GIntLit, so the pattern type, and eDOT-type. Now, eDOT-type is a singleton type, a feature of Scala which was formalized in cDOT. And what this particular singleton type tells us is that E1 and E are the very same object, of course, right? Now, based on this type, based on this binding, we can derive that int is a subtype of X in a few steps. And the way we do so is that we can derive that int is a subtype of E1.a, since E1 is of type intLit, and intLit initializes a to int. Then we can derive that E1.a is a subtype of E.a, because they are the same object. And finally, we can derive from the type of E that E.a is a subtype of X, right? So this term is well typed. And what we should also note here is that we've seen that subtyping reconstruction formally takes place entirely in subtyping. There is no separate judgment responsible for our form of reasoning. It is entirely done in subtyping. Okay, so now we will take a look at what cDOT actually looks like. First, the type forms. As promised, they correspond directly one-to-one to the types we have been seeing so far. We mostly lose a few keywords. The syntax is slightly changed, but for the most part, that's that. In the first example, we see that all type members in cDOT need to come with an upper and a lower bound. In this case, these bounds are trivial, so bot and top as appropriate, but they must always be there. And in the third example, we see that where in Scala syntax we can make a type member equal to another type, what we do in cDOT is that we just have a type member with a lower and an upper bound that are the same. And there are two type forms in cDOT which we haven't seen so far. We use path-dependent function types for functions. And in general, we may need to type objects with recursive types because an object may need to refer to its own type members in, for instance, the types of its methods. Now, compared to pDOT, there are no new type forms in cDOT. Where we did need to make additions are term forms, where first, we added a case form with an unsurprising syntax. And second, we modified object literals to be tagged. So first, let's take apart the object literal that we see. It contains three elements. First, it has an explicit binding for the self-reference of the object. Second, it contains the object's body, which is just two member initializers. And finally, it also contains the object's tag. Okay, so what's that? Why do we need to tag objects? So the way that objects are typically implemented is that at runtime they are tagged. They contain a reference to some runtime representation of their class, right? And that's because we need that to be able to tell if an object is an instance of a particular class. The way that type case patterns and the way that instance of operator work is that they inspect this runtime class representation. And classes are formally represented in cDOT as type members. And so our choice here was to tag object literals with a reference to a type member. Now this reference is also a type. So objects also must be typable with the type they are tagged with. This is necessary for soundness. And finally, case terms are reduced by comparing the tag and the pattern to see if they are the same. Okay, and in addition to that, we also make some improvements to the typing rules of pDOT, as well as the reduction rules, but those aren't that relevant to subtyping reconstruction. Okay, so now on to the formal representation of subtyping reconstruction. As promised, it all revolves around subtyping rules, which are for the most part standard for the type forms that we have. And to support subtyping reconstruction, we have two concepts. First, we have subtyping assumptions, and second, we have subtyping inversion. So, subtyping assumptions. They as a concept were present in the original DOT system. In DOT systems in general, every binding with a type member introduces subtyping assumptions, which can be reflected in the subtyping judgment. These assumptions might be trivial, but they are always introduced. So when we were typing eval before, based on our type of E1, we have introduced int subtype of X as an assumption, right? That was an example of a subtyping assumption. And in general, if we have a context with a term variable X that has a type member with a lower bound S and an upper bound T, then in that context, we can conclude that S is a subtype of T, right? We trust the relationship between the bounds as an assumption, as we take it as a given. And what's quite interesting here is that formally, subtyping assumptions are orthogonal to case forms, right? As we have seen in the eval example, the typing rule for case just assigns useful types to the pattern-bound variables. However, subtyping assumptions can be introduced by an arbitrary object binding, not only the one bound in a pattern. And second, as a second concept that supports subtyping reconstruction, we have subtyping inversion. So to sum it up in one sentence, in cDOT subtyping rules, we have internalized subtyping inversion lemmas, because doing that lets us derive more relationships from subtyping assumptions. So we see two derivations which illustrate the idea. With subtyping inversion, if we have as an assumption that list of S is a subtype of list of T, we can derive that S is a subtype of T, right? Now, normally, we would need that judgment as a premise to derive the second judgment, to derive our conclusion. However, subtyping inversion, or rather, subtyping inversion simply lets us invert this judgment, right? So, again, it's just subtyping inversion lemmas, but internalized as subtyping rules. We have three rules like that. And actually, as simple as this might look, that's actually it. This is all that we need formally to model subtyping reconstruction. And in the final part of this talk, I would like to talk about reconnecting with existing theory. So what we also do is that we show that we can translate lambda 2 gmu terms to cDOT terms while preserving their types. So lambda 2 gmu is a classical calculus that supports GADT reasoning. And as we will see, this translation means that subtyping reconstruction subsumes classical GADT reasoning. So the interesting part here is that typing judgment in lambda 2 gmu has the form we can see on the slide. Delta is an additional fragment of context that contains type equality assumptions. And these assumptions are introduced explicitly by the typing rule for case forms, right? So where in cDOT we had assumptions be a part of the normal typing context, in lambda 2 gmu, we have a separate context fragment that holds them. And the way we make use of this delta is that we have this TyEQ rule, which might look similar to subsumption, but But it uses this type equivalence premise, which is based on reasoning about substitutions which solve delta. So this is a different basis. This is a different formal basis than the sort of reasoning we have in cDOT, and yet we show that we can translate well-typed lambda2GMU terms to well-typed cDOT terms. And so since cDOT supports subtyping and data type hierarchies of arbitrary depth, unlike lambda2GMU, that means that we actually subsume classical GADT reasoning. And there is more that we show in the paper, naturally, but I'm already out of time. So just one thing that I would like to highlight is that we also give an informal description of subtyping reconstruction as implemented in DOT. Thank you very much for your time, and I'm happy to take questions.
Thank you. Yep, back there.
Hello. This is probably a very stupid question, but you notice that when you implement the generic class like expr of t, there has to be one value for t. You can't implement expr int and expr string simultaneously, right? Like you can't have an object that is of both type expr int and expr string.
So actually in Scala, that's for the covariant expr that's actually possible, because we can have an object that implements expr for an intersection of int and string.
Would that make any sense?
For expr, no. But in general, it's about mixing, like being able to mix in traits, right? I mean, imagine that we have one trait that extends a list of int, and we have another trait that extends list of string, and we somehow want to mix in those two traits in one object, right? And Scala says that yes, we can do that.
Yeah, but you'd still only implement each method once. You wouldn't implement one for the expr int version and one for the expr string. Because like I've seen this in Rust, where you implement the trait twice and you have two different implementations of each method.
Well, so in Scala, we would need to have just one implementation of every method.
Thank you.
Any more questions? So I will ask one. So how does this solution apply to these other languages you listed at the beginning of your talk? Would they also apply, or they are only useful for Scala?
Well, so we only have a Scala implementation. However, the calculus we have seen can model terms from these other languages, right? So it also acts as an argument that in these other languages, we can have a similar form of reasoning, and it would still be sound.
Is there some kind of explicitly typed version of this language with, more like F omega or F bounded polymorphism, more explicit version of the calculus than the surface language like you are showing? Something smaller
something smaller.
Something small called calculus, right?
Right. So I mean, as
there's a similar work done in high order functors in ML and with type components.
Right.
GADT,
so
yeah.
Thank you. The goal in this work was to have a calculus which can be used as a basis for fully fledged object-oriented languages. So we intentionally chose to base it on something like cDOT, which has many features, so that it would be suitable as such a basis. But in principle, as future work, something like that very much could be developed.
All right. Thank you. Thank you again.